When making your Versa method, you will need to enter values for each of these parameters. When you click on the value, it will give you a little description of what the parameter is and any maximum and minimum values. But we're going to go through each of these parameters today in a little bit more detail. So first of all, we have the GC cycle time. This is the total GC runtime, including cooldown used to synchronize Versa injection time with the GC ready. The Versa uses a GC cycle time to calculate when to start the next file. The GC cycle time allows for the highest throughput of samples as well as ensures that all samples see the same thermal exposure time. The GC cycle time, which is entered by the user, is from ready to ready. This means from the time when a run is started until the GC becomes ready again, the analysis plus the cooldown and the equilibration time. When determining this time, it is recommended you estimate high. This is to take into account any room temperature changes that may occur that will affect the GC cooldown time. Please note here, if the GC is not ready in the time the user inputs, the Versa will wait with the sample pressurized until the GC becomes ready. This potentially results in the valves being exposed to too much thermal exposure time. Valve oven temperature. This is the temperature setting for the 6-port valve and sample loop. The temperature of the loop also indirectly affects the mass transfer to the column. Lower valve oven temperatures result in a gas with a higher density in the sample loop prior to transfer. The higher density increases the amount of analytes on the column, therefore increasing sensitivity. Valve oven temperatures need to be selected with both sensitivity and carryover in mind. Low valve oven temperatures may result in higher sensitivity, but also higher carryover. The recommended starting points for the valve oven temperature are 0 to 5 degrees above the sample equilibration temperature. Transfer line temperature. This is the temperature setting for the heated transfer line. The transfer line temperature should be set to the same or 5 to 10 degrees above the valve oven temperature. Platen/sample temperature. This is the temperature the sample will be heated to reach equilibrium prior to sampling and injection. One of the factors that has a direct influence on the K value is platen/sample temperature. Typically, the higher the temperature, the lower the K value. As the sample temperature increases, the solubility of the analyte increases, but the vapor pressure also increases. The vapor pressure increase will have a larger effect on the K value than the solubility increase, therefore forcing the equilibration towards the gas phase. It should be noted that there are typically limitations to the sample temperature due to the matrix. It is not recommended to exceed temperatures above 15 degrees below the boiling point of the matrix. For example, if the matrix is water, then it is not recommended to exceed 85 degrees Celsius for the Platen sample temperature. Another negative effect associated with elevated Platen sample temperatures is sample degradation due to the temperature. Thermal liable compounds can break down at high temperatures, causing reduced response. Platen temperature equilibration time. This is the time the platen waits at set point to reach thermal equilibrium before analysis starts. Platen equilibration time is the time the Versa will wait for the platen to equilibrate at the set temperature. The main functionality is when multiple platen temperatures are being used within a schedule or when the unit is being powered up to run. If the same platen temperature is always being used, this equilibration time can be set very short, such as 0 to half a minute. Please note, if platen temperatures are going to be changing throughout a schedule, it is strongly advised to schedule methods to start at the lower temperatures and move to the highest temperatures. The platen heats much more quickly than it cools. Therefore, by ordering samples to go from lower platen temperatures to higher temperatures, a higher sample throughput is achieved. Sample equilibration time. Time needed to heat the sample for headspace equilibration. After the platen/sample temperature has been selected, it is critical to select a sample equilibration time that allows the sample to reach equilibrium prior to the sampling step. Allowing the sample to reach equilibrium prior to sampling allows for the method to be robust. In rare cases, mainly when working with solids that exhibit low diffusion characteristics, the sample may never reach equilibrium. Mixer. This is the sample mixing prior to sampling, so off or on. Mixing level. This value corresponds to the speed that the mixer will turn. The RPM at which the mixer turns can be adjusted by changing the mixer speed. The sample should never be mixed hard enough to allow sample to be splashed onto the septa, so for the Versa you have slow, medium or fast options. Mixing time. This is the amount of time the sample is mixed. Mixing the sample typically helps reduce the total thermal exposure time needed to allow the sample to reach equilibrium. This is especially true when analysing liquid samples. The mixing step increases the gas-to-liquid interface in the vial, therefore reducing the distance that the analyte needs to travel to reach the gas phase within the vial. Mixer stabilization time. This is the amount of time the sample waits after mixing before proceeding to allow the sample to re-equilibrate prior to sampling. Once the sample has been mixed, this allows the sample to re-equilibrate after the mix step. This parameter typically is set 30 seconds to around 2 minutes. Pressurize. This is the amount of gas added to the vial to ensure loop fill flow. Vial pressurization mode pressurizes the vial with gas prior to allowing the sample to flow through the loop. The vial needs to have enough pressure to allow it to adequately and repetitively fill the sample loop. Typically, the sample will generate what is called a static vial pressure during the sample equilibration step. This pressure will normally range from half to 11 psig depending on the sample. To determine the pressurization setting, the static vial pressure needs to be determined. Pressurized time. This is the amount of time to reach pressurization setting. Pressure equilibration time. This is the amount of time sample waits after pressurized before proceeding. This time allows for the gas added during the pressurization step to mix and equilibrate within the vial prior to sampling. Loop fill pressure. This is where a pressure setting is applied to loop fill mode, which controls the pressure within the loop prior to transfer to the GC. The higher pressures in the loop result in more mass in the loop. This directly affects sensitivity as well as eliminates variation in atmospheric pressure. Typically, a loop fill pressure is selected that is 2 to 3 psig below the vial pressurization setting for a 1 ml standard loop. When using smaller loops, this pressure delta can be reduced, and when using larger loops, the delta may be increased to allow for the loop to be correctly filled. Loop fill time. This is the amount of time required to allow the vial pressure to vent through the loop. Inject time. This is the amount of time for when the 6-port valve is rotated, allowing carrier gas to sweep through the loop and transfer compounds to the analytical column. There are two critical factors that need to be known to properly set the inject time: the GC carrier gas flow rate and the loop size. It is recommended that a minimum volume of 3 times the loop size should be flushed through the sample loop during injection to completely transfer the sample gas to the GC. To determine the proper time, take the loop volume multiplied by 3 and then divide by the carrier flow rate. We've spoken through all the parameters that you need to input a value for when creating a method for your Versa. For more information on how to build your method and schedules, please see our other videos.